If hyperspace were real, what dangers might lurk in the great unseen? And could it ever be more than a sci-fi dream? From wormholes to warp drives to hyperspace lanes, science fiction has given us imaginative ways to cheat the cosmos. But is it even possible? And what is hyperspace anyway? Grab a drink, a snack, give the like and subscribe buttons a smack, and let's explore hyperspace. Hyperspace is an intriguing concept that bridges the gap between science and imagination, often serving as a stand-in for faster-than-light FTL travel in speculative stories. Its presentation varies widely, appearing in major science fiction franchises like Star Wars, Isaac Asimov's Foundation series, and TV shows such as Babylon 5. At its core, hyperspace refers to an alternate dimension or higher dimensional space that allows travelers to bypass the normal constraints of our universe. Instead of being restrained by the cosmic speed limit, the speed of light, hyperspace offers a theoretical shortcut, enabling rapid journeys between distant points in the cosmos. While the term hyperspace doesn't have a direct and universal counterpart in current scientific models, it draws inspiration from real physics concepts such as higher dimensions in string theory, wormholes, or the manipulation of space-time. Its interpretation in science fiction reflects as much narrative creativity as scientific plausibility. In science fiction, hyperspace is not just a tool for traveling faster than light, it's a rich narrative device that shapes the worlds and stories built around it. In Star Wars, hyperspace lanes offer established routes for interstellar travel, bottlenecks for trade, piracy, and battle. In Dune, the Spacing Guild's forward space ability allows instantaneous movement through a mysterious, navigationally demanding dimension. Meanwhile, Babylon 5 envisions hyperspace as a dangerous, alternate realm where navigational beacons are essential to avoid getting lost, and ancient ruins drift in its void, waiting to be encountered by unwary or adventurous travelers. Ironically, hyperspace from Isaac Asimov's Foundation, widely regarded as the top sci-fi book series of all time, is probably the least exciting. You engage the engine after performing the complex calculations and disappear and instantly re-emerge, hopefully at the right destination, but there's no passage of time or explanation for how the system works. I often recommend that approach to sci-fi writers. Don't waste time trying to explain a fantastic system whose only purpose is to get around the huge problem of getting around the huge immensity of space and human timescales. This approach avoids unnecessary exposition and the risk of embarrassing math or physics mistakes. However, it also forfeits the chance to embrace the intrigue that a mysterious shadow reality might add to a story. To strike a balance, we will delve into how hyperspace is depicted in some of the more detailed works of fiction, providing inspiration for those crafting stories set in strange, non-Euclidean realms or dimensions existing at right angles to our own reality. Of course, our main focus will be on exploring whether hyperspace holds any genuine potential as a method for traversing the galaxy without taking the scenic route, or if it is truly just science fiction. The idea of venturing into a dimension beyond our comprehension resonates deeply with our innate curiosity and thirst for exploration. Hyperspace also comes with its own set of fictional rules, navigation challenges, unique physics, and even strange entities, making it as much an interesting element in these stories as the ships or people that use it. Drifting helplessly off a beacon into uncharted hyperspace and encountering space kraken living there, or ancient and abandoned stations, or relics left in deep hyperspace make for exciting tales. But its key appeal lies in offering a solution to the vastness of space while raising profound questions about what lies beyond our understanding. Notably, many depictions of hyperspace accomplish this without outright violating Einstein's theory of special relativity. The earliest science fiction reference to hyperspace for travel appears in Hugo Gernsback's Amazing Stories circa 1931. However, the term itself predates modern sci-fi, tracing back to the 19th century, where it was used to describe higher dimensional spaces. This was before Einstein developed his theories of relativity, during a period when even some serious scientists speculated that stage magician tricks or complex knots might be exploiting four-dimensional space to function. They weren't thinking about it for space travel, though. In the early 20th century, science fiction didn't grapple much with the true scale of the universe. The term galaxy is old, dating back to ancient Greek civilization, and first appeared in English in Geoffrey Chaucer's works for describing that big dense band of stars in the sky, the galactic disk, and eventually began realizing we were in that disk. However, it wasn't until Edwin Hubble's work in the 1920s that humanity realized galaxies were distinct islands in a vastly wider universe, and not particularly spherical islands either. Before that, the universe was often assumed to be infinite in size, eternal in age, and relatively homogeneous in distribution. As theories of special and general relativity became more widely known and the scale of the galaxy was better understood, science fiction began to reckon with the challenge of interstellar travel. Writers introduced various mechanisms to explain FTL travel, from warp-style drives like those in Star Trek, which allow faster-than-light movement within normal space, to devices that take you instantly to another place by folding space itself, and those that involve jumping into an alternate dimension, traversing it, and emerging back into normal space at a congruent point. I don't want to spend too much time explaining why we can't travel faster than light under normal circumstances. We've covered this in detail in our FTL Faster Than Light series, but a quick overview is appropriate. The term light speed is not the most accurate name for this universal limit. Light, along with other massless particles, travels at this speed because they lack mass. Nothing with mass can ever reach or exceed it. We first measured the speed using light, so the term stuck, but a more accurate description would be the speed of causality, as it represents the maximum rate at which useful information and cause and effect can propagate through space-time. Thinking of it this way makes it intuitively clear why exceeding the speed of light would inherently imply the ability to travel backward in time and alter the past. Things with mass experience time. Massless particles, like photons, do not. As an object with mass accelerates, more of its total energy transitions from resting mass energy, as described in E=mc², into other forms, such as kinetic energy. You've probably heard that as you speed up, your mass appears to increase, meaning that every additional increment of speed requires more energy to accelerate further. This process continues exponentially, requiring infinite energy to reach the speed of light. Modern physics tends to avoid the distinction between rest mass and relativistic mass, as it's more accurate to think of the added mass as kinetic energy. Energy in all its forms bends space-time and requires effort to accelerate or manipulate, whether that energy is mass, kinetic, thermal, or rotational. For example, a spinning or heated object requires more effort to accelerate than its non-spinning cooler counterpart. Here's the key idea. At everyday speeds and conditions on Earth, nearly all the energy in objects exists as mass energy. For example, a glass of water contains an immense amount of mass energy, more than is what is released in a typical atomic bomb, while only a tiny fraction of its energy is from thermal, kinetic, or gravitational potential sources. This is why you and I, along with that glass of water, experience time at nearly its maximum rate. Virtually all our energy is tied up in mass, and that mass portion is experiencing time. As an object speeds up, heats up, or spins up, the proportion of its energy coming from mass decreases. Same mass, but more total energy. Consequently, it experiences time more slowly. For instance, if half an object's energy is mass energy, it will experience time at half the normal rate. However, no matter how fast you accelerate, heat, or spin an object, a portion of its energy will always remain tied to mass, meaning it will always experience time, albeit at a slower rate. Complete time dilation, like what photons and gravitons experience, remains out of reach for anything with mass. I should note the reverse is true too, as even a low mass and cold object far from any galaxy's gravity has at least some non-mass energy, and thus some time dilation. To contemplate going beyond the speed of light, we need to consider concepts like imaginary mass, akin to imaginary numbers such as the square root of -1. Note that this is imaginary mass, not negative mass. Negative mass also plays a theoretical role in bypassing light speed, but in a different context, often involving wormholes or warp travel. However, neither negative mass nor imaginary mass is inherently required for hyperspace concepts. Hyperspace as a fictional construct comes in many forms, Again, in mathematics, it's an order term used to describe higher dimensional spaces, where structures like tesseracts can theoretically exist, the four-dimensional equivalent of a cube, much as a cube is a 3D version of a square, which is a 2D version of a line, and that a 1D version of a point, I suppose. The most common interpretation in science fiction is that hyperspace is a distinct kind of space connected to our universe, or vice versa, where travel is faster or distances are effectively shorter. But sometimes, hyperspace is portrayed as another universe with slightly different properties, like a faster speed of light or being smaller or younger compared to our universe's size and age. For instance, imagine you could tether yourself to a specific position in our universe, then leap back to an earlier period where everything was closer together due to Hubble expansion, the stretching of space itself. You could theoretically travel to another location near the speed of light, then return to the present and emerge very far away. This works because in the earlier universe, those 2 points were closer, and over time, Hubble expansion spread them apart. Notably, Hubble expansion allows distances to increase faster than the speed of light, since it is space itself that's expanding, not objects or information moving through it. However, this method inherently permits time travel, which complicates causality, cause and effect. To sidestep such issues, hyperspace must instead involve traveling to a parallel universe that is congruent to our own, a universe where conditions align with ours in certain key ways. But what is a congruent universe? In geometry, two shapes are congruent if they are the same size and shape, even if they are rotated, flipped, or moved. For example, two triangles are congruent if all their angles and side lengths are equal. A map, ideally, is supposed to be congruent to the place it's drawn on, though flat maps and spherical planets make that tricky. More generally, congruency means in agreement or in harmony, and in physics some systems that share similar properties are alignments. There's no official concept in physics for a congruent universe, but generally a congruent universe is a hypothetical parallel universe that shares a high degree of similarity with our own. It might have identical physical laws, spatial structures, and cosmological properties, but with slight variations that make it distinct. In this context, a congruent universe would be one that matches our own at a specific moment in time, like an overlay of our universe's past or future state, but without the causal paradoxes introduced by direct time travel. This congruence implies a connection that allows you to map locations in one universe onto corresponding locations in the other and vice versa. Imagine if you could step onto a physical map of your state or country, walk a few inches to another spot on the map, and then emerge at the corresponding location in the real world. However, your travel would be restricted to those mapped points. You couldn't step from Los Angeles to Tokyo on the map and reappear in New York instead. This mapping ensures consistency and prevents arbitrary jumps, maintaining a logical framework for travel. Faster-than-light travel would revolutionize our place in the universe, but are there ultimate scientific limits like FTL and hyperspace that even science cannot overcome? In The End of Science, our Nebula exclusive episode, we ask whether science itself might have an end and barriers it cannot breach. Could we one day reach a point where we understand everything, where no mysteries remain, or will new frontiers always await just beyond the next horizon? Join us in The End of Science, available only on Nebula. Nebula is the largest creator-owned streaming platform, where every SFIA episode airs early and ad-free, alongside exclusive content from myself and many other fantastic creators like Real Engineering, Simon Clark, and Angela Collier. Get access to awesome Nebula originals like Tech Autos, How Circular Space Stations Conquered Sci-Fi. Sign up at go.nebula.tv/Isaac Arthur using my code IsaacArthur to get 40% off an annual plan. That is $3 a month. Nebula also offers lifetime memberships and gift options, so you can share exclusive content like The End of Science with friends and family. And for new Nebula subscribers, you can get access to guest passes. Share your passion for Nebula with friends and family. With them, they can get free and easy access to all Nebula content for a whole week. So go subscribe to Nebula and give a week of exclusive content with guest passes using the link below to get 40% off the annual plan. And now, let's warp back into the mysteries of hyperspace. Forwarding space generally assumes a different approach. Imagine forwarding a 2D map so that 2 points touch. In this case, the forward occurs through a higher dimension, our 3D universe. A forward space drive extends this concept, folding 3D space through an even higher dimension or hyperspace so that 2 points touch. However, how you jump between those points on the folded map is often unclear. Same for where you are getting the energy to fold that map, which is not likely to be free. Additionally, if those 2 points actually merged or stuck together, significant issues could arise, such as gravitational interactions pulling nearby stars or objects together, potentially causing catastrophic events like collisions or explosions. So you probably only want a temporary overlap and fold. Maybe space-time would resist being folded, and it takes a lot of energy to fold and press spaces together and then spring back to an unfolded state. We deep dived this more in our episode Folding Space a few years back. In scenarios involving congruent spaces, the assumption shifts. Neither the space involved is hyperspace itself. Instead, both exist within a broader hyperspace. Think of it like a pair of maps in an atlas, where the atlas itself is a 3D book or part of a library filled with maps of varying sizes and scales. In this type of hyperspace, a congruent universe might be one where distances between points are compressed, or the topology is altered in a way that makes travel faster or more direct, or the speed of light or causality is simply higher. That probably would have real consequences on objects that made the jump too, as it might imply entirely different behavior of mass, which might be a problem since your spaceship and person are made from it. In this case, you wouldn't be time traveling. Instead, you'd be navigating through a snapshot of a universe with altered spatial properties, but still aligned with our own in essential ways. This alignment or congruence ensures you could safely re-enter our universe at a corresponding location without creating paradoxes or disrupting the natural order of either space. There's also cosmological models in which this might be viable, like if string theory is right, in which case you not only have extra dimensions with many universes, like yet unlike our own in them, including different particles and physical constants, but interactions between those spaces. Indeed, it is assumed a collision or intersection of various branes can cause a Big Bang event, and something smaller scale should be possible too, as might practical travel between them. And as they do occupy locations in a wider hyperspace, shortcuts might be possible. See our Untangling String Theory episode from earlier this year for further discussion. It is also worth noting at this point that brane cosmology theory allows for a sort of higher dimensional area between universes, often called the bulk, which is an actual mathematical hyperspace. It is to our space as is a hypercube to a cube to a square, or a sphere to a circle. There has been some speculation about using this for FTL, but of course it's highly conceptual at this point, as is everything else involving hyperspace. If true though, this may allow travel not only to other parts of our universe's brane, but other universes as well. It's one possible framework for how all sorts of portals and other intra-universal higher dimensional shenanigans might be explained. Incidentally, you could think of our universe as a piece of paper, which is basically 2D but has a tiny 3D component, and we talk about extra dimensions that are compactified or too small for use to see. For string theory or M theory, that's the idea, that we are a 3D sheet of paper in a 4D universe. Or even a 5D version of a string, itself basically 1D but having a small component of 2 other dimensions, not just one smaller hidden dimension, or sometimes 10, 11, or 26 total dimensions. As an aside, it's also worth noting that any spaceship traveling through higher dimensional hyperspace might be torn to shreds. This is due to the distribution of forces over distance squared versus cubed. Forces like gravity or the strong nuclear force are predicted to dissipate much sooner the more dimensions you add. So much so all molecules may not hold together in a 4D space like the bulk. You would dissolve into elemental particles. This would require travelers to be contained within some sort of bubble or tube of flat 3D space as it made its voyage, which we might call a subspace. Conceptually, imagine you are a stick figure drawn on a piece of paper. You cannot survive without being on a piece of paper, you must be drawn on something. So if you want to fly to the other side of my office, I must fold the piece of paper you're on into a paper airplane and hurl you there. That paper airplane is the safe 3D bubble, and my office is the bulk interpretation of hyperspace. Again, see our string theory episode from January for a detailed but simplified explanation of string theory and M theory, which is where the brane's concept originates from. Brane as in membrane. This and other concepts of hyperspace allows for speculative faster-than-light travel while avoiding the pitfalls of altering history or violating causality, a recurring challenge in many FTL theories. It also opens fascinating possibilities for how alternate dimensions or realities could intersect with our own, providing a fresh framework for storytelling and theoretical exploration. But both versions, folding normal space through hyperspace or traveling between two parallel universes existing in a wider hyperspace, are different from notions of jumping to hyperspace and traveling there, like we see in Babylon 5. This is probably our most fleshed out example of this style of hyperspace in a major sci-fi franchise, so let's delve into it a bit. Great show too, even if the CGI doesn't hold up well on modern screens. In Babylon 5, hyperspace is depicted as a separate dimension that allows for faster-than-light travel. Travel to and from various parts of the galaxy is done by first entering hyperspace, then leaving at the right place. Hyperspace is accessed through jump points, created by powerful devices called jump engines. These engines open a rift between normal space, referred to as real space, and hyperspace. Larger vessels, such as warships or capital ships, have built-in jump engines, which is handy for avoiding impossible military bottlenecks that jump gates would otherwise be, while smaller ships or ancient civilian craft rely on pre-existing jump gates scattered across the galaxy. Many are leftovers from ancient and mysterious races who don't seem to hang around anymore. Hyperspace is a chaotic and unstable dimension filled with swirling energy fields, making navigation extremely challenging. Ships rely on beacons, navigation points that provide fixed coordinates, to plot courses through hyperspace. Without these beacons, navigation becomes virtually impossible, and ships risk becoming lost forever. Advanced civilizations, like the Minbari, are capable of navigating hyperspace more efficiently due to their superior technology, and the even more advanced and older Vorlons are secretly the original designers of the technology. When we encounter another species that's equally old, we see their method of entering and exiting hyperspace is very different from what all the other races use, based on that original Vorlon design. It is also strongly implied that hyperspace extends beyond our own local galaxy, but not well, making intergalactic travel impractical. We see something similar with the warp travel used in Warhammer 40,000, limited to in-galaxy travel only, and in that case the hyperspace, or warp, is more or less literally hell, which is also the case in the film Event Horizon. In both B5 and 40K, hyperspace is not a safe or benign environment. Ships without proper navigation or shielding can become lost or destroyed. In 40K, the primary beacon is situated on Earth and is fueled by Fediate telepaths, which makes sense since the warp is a psychic realm, akin to the astral plane, which can often be used for travel in fantasy series, a realm of the mind. But in B5 they also have telepaths, and they do have a stronger ability in hyperspace, though why is never explained. Abandoned or derelict ships and ancient structures are known to drift in hyperspace, creating a sense of foreboding and danger for travelers, and shows up in both the spin-off series Crusade and the TV movie Third Space, where they find a relic floating in hyperspace that turns out to be a gateway to yet another realm beyond normal and hyperspace, and full of murderous, telepathic, and xenocidal aliens. I hadn't really noticed until I was writing this how many parallels Babylon 5 and Warhammer 40K have in their hyperspace setups. Both feature the concept of a treacherous alternate dimension used for faster-than-light travel, rife with dangers and navigational challenges. Warhammer 40K also shares the idea of navigators with the Dune franchise, mutants who can chart a path through the twisted reality of FTL travel, though calling it sharing might be generous, as Warhammer 40K clearly borrows heavily from Dune. In Babylon 5, we later discover there are organisms native to hyperspace, or at least assumed to be, which adds to the mystery and danger of this alternate realm. Meanwhile, Dune's navigators aren't exactly navigating in the traditional sense. As best as we can tell, the calculations required for hyperspace travel are near impossible, and their society has banned computers capable of performing them. Instead, navigators rely on limited precognitive abilities to see potential futures and presumably pick the one where pressing the forward space button does not result in their fiery demise. In some settings, there's not one hyperspace, but actually several layers of it, In the Black Ocean series by J.S. Morin, the setting's hyperspace, called astral space, had several layers of it, and the deeper you went, the faster you could travel, but also the more dangerous it was to navigate. Something similar applies in David Weber's classic military sci-fi series set around Honor Harrington. Multiple levels, so civilian and commercial traffic in Black Ocean were at the more shallow levels. And then military ships used deeper lanes, while suicidally daring ships went even deeper. Amusingly, in that series, the magical hand-waving explanation for hyperspace was literally magic, and accomplished by wizards casting spells and enchanting drives. Another setting that toyed with the idea of multiple hyperspace levels was the Cultural series by Ian M. Banks, which dealt with both an ultraspace and infraspace, which was respectively above and below our setting of space. In most of these settings, it is assumed that gravity bends space in a way that makes hyperspace jumps unpredictable or hazardous. Often celestial objects act as navigational hazards even while in hyperspace, suggesting a natural overlap or interplay between the two realms. This shared concept not only adds realism to these fictional universes, but also underscores the universal appeal of blending the known dangers of space with the eerie unknown of alternate dimensions. I would say that is unrealistic, but if you are able to enter one from the other, that implies some use of natural phenomena that you have discovered and tamed, that these two places do interact with each other, at least minimally. I should note the term non-Euclidean space gets used a lot in sci-fi topics like this, and since we are a science show that uses sci-fi as examples, not a sci-fi lore channel, as much as I enjoy that, I feel like I should explain that term as it gets abused a lot. Euclid is the Greek mathematician who gives us the 5 axioms of regular geometry, which are 1. A straight line can be drawn between any 2 points. This postulate establishes the concept of a straight line and states there's a unique line that connects any 2 distinct points. 2. A straight line can be extended indefinitely in both directions. Lines are infinite in Euclidean geometry. They don't have endpoints unless explicitly defined as segments, or unless physical reality ends, like a finite universe. 3. A circle can be drawn with any center and radius. Given a point, center, and a distance, radius, a circle can always be constructed. This generally extends to higher dimensional equivalents like a sphere or hypersphere. 4. All right angles are equal to one another. This postulate ensures the concept of a 90-degree angle is consistent across the entire geometry. And 5. If a straight line crossing 2 other straight lines forms interior angles on the same side that sum to less than 2 right angles, the 2 lines, if extended indefinitely, meet on that side. This is also known as the parallel postulate. It implies that if 2 lines don't meet, the angles formed by a third line crossing them must sum to exactly 180 degrees. We also have 5 common notions from Euclid that are worth mentioning. 1. Things equal to the same thing are equal to each other. For instance, 1, 2 halves, and 3/3 all represent the same value. 2. If equals are added to equals, the results are equal. 3. If equals are subtracted from equals, the remainders are equal. 4. Things that coincide are equal. And 5. The whole is greater than the part. As long as these axioms apply, you are dealing with Euclidean geometry. Any geometry that violates one or more of these axioms, especially the parallel postulate, falls into the realm of non-Euclidean geometry. This can range from the mundane to the deeply abstract, and all the more so if we throw those 5 common notions into play and assume a reality where basic math can start breaking down. But it's not always arcane. For example, consider a set of train tracks, 2 rails that are parallel but merge in the distance due to perspective. On a flat 2D map, these lines would remain parallel. However, if you folded the map at an angle, these 2 lines would cross. While this isn't particularly profound, it illustrates how altering the space where geometry is applied can break Euclidean rules. Another case involves spherical geometry. On a sphere like Earth, 2 parallel lines on a 2D map might appear to stay equidistant. However, on the actual 2D surface of the planet, these lines would form great circles, which eventually intersect. You could theoretically build train tracks around the planet that stay a few feet apart, but they would gently curve along the sphere, not remain perfectly straight. These deviations from Euclidean principles highlight how the nature of space itself can alter rules of geometry, and they become even more profound under relativity, gravity, and warped spacetime. It's no surprise that authors often invoke the term non-Euclidean, though it tends to be used in a vague or dramatic sense. In works like H.P. Lovecraft's Cthulhu mythos or Warhammer 40,000, the term suggests a realm of chaotic or incomprehensible rules, where familiar logic breaks down. However, in most practical applications, non-Euclidean geometry usually just means that fifth axiom about parallel lines does not apply. We encounter non-Euclidean geometry far more often than we realize, and it's not as strange as it might sound. For instance, many video games create simulated universes with bizarre geometries. My 6-year-old son, whose name happens to be Geometry, recently started playing the old Dragon Quest games on Nintendo, or the tablet version. In those games, the 2D map allows players to sail east or west and emerge on the other side, which makes sense. However, sailing north or south does the same, meaning you reappear halfway around the planet without passing through a pole. This sort of map wrapping, while conceptually odd, was a common feature of older games. This is trivial compared to what's possible without even adding extra dimensions. For example, in 3D games, designers often create environments that players can explore but that don't connect physically to each other. These disconnected spaces can be logically mapped in a hyperspace-like structure, allowing for seamless transitions between them. This shows how non-Euclidean principles can be applied creatively, both in storytelling and in practical simulations, without requiring a full departure into incomprehensible madness. My other son, with the more mundane name of Chris, is currently obsessed with Star Wars, particularly the Clone Wars, which features something called hyperspace lanes. These conveniently allow the galaxy far, far away to be usefully displayed in a two-dimensional manner. Hyperspace lanes are stable paths through hyperspace, free from black holes or other disruptive influences, which would otherwise make navigation hazardous. Black holes and singularities are reasonable concerns for hyperspace topologies, since topology becomes unpredictable around singularities, as well as cuts, corners, and other abrupt changes. Some of these hyperspace lanes are long-lasting and well-traveled, earning iconic names like the Corellian Run or the Hydian Way. These routes are patrolled and form the backbone of intergalactic civilization. However, most lanes are much shorter, requiring ships to periodically drop back into real space to check their position and recalculate their path. This limitation confines travel primarily to within the galaxy, which is a deliberate plot device to minimize intergalactic activity. The Yuuzhan Vong, one of the few exceptions, are no longer considered part of the official canon, though I think they were a cool story arc. Interestingly, hyperspace in Star Wars seems to be significantly affected by gravitational phenomena, making the deep core of the galaxy incredibly dangerous and difficult to navigate. This region, like the centers of most spiral galaxies, is dense with black holes and other extreme space-time phenomena. While the supermassive black hole at the center of the galaxy is notable, it's not unique or essentially important to hyperspace navigation. The depiction of hyperspace in Star Wars is iconic, with ships traveling through an artificial pocket of real space while in it as stars flash by as streaks of light. This real space pocket conveniently avoids the complications of strange physics aboard ships during transit. It's akin to the earlier concept of a congruent universe with different rules enabling faster travel. The idea that the real universe influences your path through hyperspace makes logical sense. Navigational challenges, such as needing to drop out of hyperspace to check position and recalibrate, reflect the inherent unpredictability of long-distance travel across tens of thousands of light years, where because of the speed of light, those stars you see are not where you think you see them anymore. Even minor gravitational variables and cosmic phenomena can disrupt a predicted course, requiring frequent adjustments for safe and efficient travel. You might wonder what entering hyperspace looks like, and the simple answer is, I don't know. Without knowing its properties, it's impossible to describe with certainty, but odds are it would not be the iconic Star Wars Starstreak look. In Star Wars, it's depicted as entering a pseudo-acceleration stage where the stars blur with speed as you zip off into the distance until you wind up in a blue tunnel effect, which you can only do away from a planet's gravity, but there's no real basis for that. You could enter a higher dimensional plane at any speed, from any elevation, even in a degree of warped spacetime, so there's no need to exit that planet's gravity well either. You are, depending on your model, sliding at a right angle to reality and to somewhere else. It's a little like asking where on a building's floor plan you can put a staircase. fundamentally anywhere, as long as it's not conflicting with something else you want, like a room or plumbing. But if you ask whether a staircase is on the first floor or the second, the answer is yes. And someone looking at a staircase on the first floor and the second floor would see two very different looking objects, and a 2D map of each floor showing the staircase will not show the same thing, as a 2D image of a 3D object that basically pokes into two or more 2D spaces, the various floors or stories of a building. Nor is this the classic portal look of a 2D window, at least on our side. If you enter a 2D space, you might see a 2D window, and similarly, moving from a high dimension to ours might appear as a 3D window inside a 4D or higher space. Going into a 4D space would probably look like a sphere to us, though a tesseract or similar might be the case, and that would likely involve a weird quasi-kaleidoscope effect as you move toward it. Folding space, on the other hand, ought to look like a straight-up blend of the initial view with the incoming view, so doubling up of stars, two different planets next to each other, and so on. If you're jumping into another universe with different properties, you might get this blend, but you also might have an issue of there being no photon or photon analog in that place for you to see and detect your way around. All darkness, even by the normal boring darkness of space in general. If we are talking a congruent universe style of hyperspace, then entering or exiting might look like a strong distortion of space-time, similar to an Alcubierre drive. It might also look a lot like two-way wormholes or Stargate-style portals. Reason for the similarity being that in either case you're still leaving the local piece of the brain and breaking causality with the outside observer. A warp drive and a hyperdrive both have a certain event horizon-like effect in that regard. Alternatively, if we're talking a 4D style of hyperspace, then a strange sort of kaleidoscope effect may happen to you. I recall Carl Sagan's famous illustration of Flatland and how a ball or an apple would look passing through. All the 2D people of Flatland might observe as an object growing larger, then smaller, as the 3D ball passes through their 2D paper. Likewise, as you are plucked from this dimension and elevated somewhere else, we may see some strange and horrific effects as parts of your body and your ship are sucked into another realm before other parts. But if we're talking hyperspace as in the bulk from earlier, how does that work? How do you have a wormhole to nowhere? Well, you might not at all. For that scenario, you might have to bring a bubble of stable space-time with you, a basement universe according to some, so you never see hyperspace beyond the bubble. All an outside observer would see is you and your departing ship being pinched off from this part of reality, which may look like entering a short-lived wormhole to a basement universe before the wormhole closes. This would be a truly impressive feat of Clark-Tech engineering. Now, to close out, I thought we'd discuss the differences between warp and hyperspace and wormholes, another common sci-fi FTL. So is warp, but that's trivial. Warp drive, like in Star Trek, operates on subspace, which is a real math concept too, though Trek is a bit loose and inconsistent in its use. They generate a subspace bubble around them, which also has a real space pocket the ship itself is in. Space compresses in front of them and re-expands behind, meaning they cover less space rather than breaking light speed. The Alcubierre warp drive uses that approach via negative matter. See our warp drives episode for the details. Hyperspace and wormholes are two popular concepts in science fiction that offer tantalizing ways to cheat the constraints of interstellar travel, but they represent fundamentally different approaches, though both are pretty broad terms in both science and sci-fi. Wormhole usually refers to an Einstein-Rosen bridge specifically. Hyperspace is often predicted as an alternate or higher dimensional space that connects distant points in our universe. Travelers jump into this strange realm where distances are compressed or physics allows for faster movement, enabling them to bypass the speed of light. In contrast, wormholes are theoretical shortcuts through space-time itself, forming tunnels between two distant locations. While both ideas stretch the imagination and space-time itself, their underlying principles and mechanisms diverge significantly. Hyperspace draws inspiration from higher dimensional spaces theorized in physics, like those explored in string theory. The experience of hyperspace is often portrayed as disorienting, with unique rules and strange phenomena. In fiction, it's also a solution to the daunting vastness of space, allowing faster night journeys without violating special relativity outright. Wormholes, on the other hand, are more firmly rooted in theoretical physics, at least the ones originating from Einstein's equations of general relativity. As we discussed in our Stargates episode last year, there are other versions. The Einstein-Rosen bridges represent a possible way to connect 2 points in spacetime by bending or folding the fabric of the universe, usually by use of negative matter, which theoretically bends spacetime the opposite of how normal matter does. Normal matter compresses space and slows time. Negative matter presumably expands space and maybe speeds up time. While mathematically plausible, traversable wormholes face significant challenges, including the need for exotic matter with negative energy density to stabilize them. In stories like Stargate or Interstellar, wormholes offer a direct path from one place to another, often depicted as instantaneous travel through a tunnel-like structure. Though as we explore in our Stargate and Wormholes episodes, they are not in any way instantaneous. You have a real and lengthy journey time into a wormhole and through its throat and then out the other side, not a few moments. Both concepts come with inherent dangers and limitations. Hyperspace travelers might face navigational hazards such as becoming lost or encountering native entities, as seen in Babylon 5. It also requires advanced technology or special skills to access and navigate. Wormholes, while potentially more grounded in physics, present their own challenges. They may be unstable, collapse under their own gravity, or lead to unpredictable destinations. Their extreme energy requirements and dependence on exotic matter place them squarely in the realm of speculation too, so don't assume they are more real than hyperspace. Indeed, I'd give better odds on finding a way to pass to other universes and finding some congruence in them than finding negative matter. But for the moment, both are basically limited to fiction and highly theoretical papers with no near-term path for experimentation to prove them, let alone utilize them. Hyperspace, with its mysteries and dangers, embodies the human desire to push the boundaries and explore the unknown. Whether as a tool for traversing vast galactic distances or as a metaphor for venturing into realms beyond comprehension, it reminds us of the limitless potential of curiosity. For now, it lives in the realm of fiction, but history has shown that today's imagination often becomes tomorrow's innovation. Perhaps one day we'll step into hyperspace for real, embarking on journeys that redefine our place in the cosmos. Until then, it's a tantalizing dream, waiting for the spark of discovery to make it a reality.